The universe has undoubtedly expanded, stretching outward endlessly in the beginning. Over time, this expansion continued, but at a slower rate, leading to the universe as we observe it today. This concept is part of the inflationary theory, which is widely accepted as the most prominent explanation for the universe's origin. However, some physicists believe this theory doesn't fully account for the creation of our universe. According to some, the universe existed before the Big Bang, continuously expanding into the past and the future. While the universe is still expanding today, it was once contracting before the Big Bang. In this view, the Big Bang is not a singular explosion but more of a phase shift, a transformation that led to the creation of the universe as we know it. Some physicists suggest that this process could continue indefinitely, potentially leading to another bounce in the distant future. The idea that the Big Bang marks the true beginning of the universe is challenged by the notion that something can't emerge from nothing. This tension has been heightened by recent discoveries made by the James Webb Space Telescope, which has revealed information that conflicts with the idea that the Big Bang was the universe's definitive start. These findings raise the question: if the Big Bang wasn't the beginning, what truly initiated the universe? Did the universe come from a prior state or something even more fundamental? The concept of a universe with no clear beginning dates back to 1927, when George Lemaitre first proposed a theory suggesting the universe might not have had a definite starting point. Some experts continue to support this idea, arguing that the Big Bang represents not the birth of the universe, but merely the beginning of the observable universe as we know it today. According to some physicists, there might be evidence pointing to a nonspecific origin, and the universe could have always existed in one form or another, expanding and contracting over time. The early universe, prior to the Big Bang, was filled with a dense, hot energy that rapidly expanded during what is known as inflation, a period of extremely fast growth. After inflation, the universe transitioned into the state we associate with the Big Bang, during which it was incredibly hot and filled with radiation and particles. As the universe cooled, energy converted into matter, and the temperature dropped significantly. Throughout this process, the universe was expanding at an accelerating rate, with regions of space stretching farther apart as time went on. The expansion slowed over time, but it didn't stop entirely. The universe began to cool as well, and the formation of galaxies, stars, and other structures began. Eventually, the expansion rate began to stabilize, but the legacy of the inflationary period continues to shape the universe we see today. Despite these well-supported theories, there are some inconsistencies when we look at the cosmic microwave background, CMB, radiation, remnants of the early universe. There are 4 primary anomalies that challenge our current understanding. First, on large scales, the universe doesn't behave as expected. Light from the CMB appears to be bent and distorted by gravitational lensing, and the degree of this bending doesn't always match predictions. Second, there are discrepancies in temperature across different regions of the CMB sky, which contradicts the assumption that the universe should be homogeneous. Third, the Hubble constant, which measures the rate of expansion of the universe, seems to be inconsistent when measured at different scales. Finally, there are signs that the structure of the universe is not as uniform as it should be, with some regions showing greater or lesser densities than anticipated. These anomalies suggest that there may be more to the universe's origin and development than we currently understand. While the Big Bang theory remains the leading explanation, the James Webb Space Telescope's discoveries challenge us to reconsider what we know about the universe's past. The idea that the universe had a clear beginning is increasingly being questioned, and future research may offer new insights into the true nature of our cosmos. The concept of the Big Bang, an enormous explosion believed to mark the beginning of the universe's development, has long been a cornerstone of cosmology. However, the true story of the universe's origins remains uncertain, with ongoing discoveries challenging and broadening our understanding of how it began and what might lie beyond the Big Bang theory. The idea of cosmic beginnings took shape in the early 20th century, emerging from crucial observations and theoretical advancements in physics and astronomy. One of the earliest proponents of this theory was Georges Lemaitre, a Belgian physicist and Catholic priest, who proposed in 1927 that the universe began as a primordial particle that expanded from a single point. This concept gained further support with the discovery of cosmic microwave background radiation, CMB, in 1964, providing solid evidence for a hot, dense phase in the early universe. According to the Big Bang theory, the universe originated approximately 13.8 billion years ago from an incredibly hot and dense state. In a fraction of a second, the universe underwent a rapid expansion known as cosmic inflation, during which space itself stretched faster than the speed of light. This period of inflation, proposed by physicist Alan Guth in the 1980s, helped explain several puzzling aspects of the universe, such as its large-scale uniformity and the absence of certain relics predicted by earlier models. As the universe continued to expand and cool, particles like protons, neutrons, and electrons began to form. In the first few moments after the Big Bang, nuclear reactions fused light elements like hydrogen, helium, and lithium. This period, known as Big Bang nucleosynthesis, is responsible for the elemental composition of the universe as we observe it today. Over the next millions of years, the universe entered a radiation-dominated era, during which photons of light were scattered by free electrons. The release of these photons marked the formation of the cosmic microwave background radiation, which now fills the entire universe and serves as a snapshot of the cosmos when it was just 380,000 years old. The universe continued evolving over billions of years, with gravity playing a central role in the formation of structures such as galaxies, galaxy clusters, and cosmic filaments. Eventually, stars formed from clouds of gas and dust, initiating cycles of nuclear fusion that released energy and created heavier elements through stellar nucleosynthesis. Despite its comprehensive framework for understanding the universe's expansion and early development, the Big Bang theory raises unresolved questions. For instance, what existed before the Big Bang? Was there ever a time when the laws of physics as we know them did not apply? These questions push the limits of our current understanding and fuel ongoing research in theoretical physics and cosmology. One intriguing possibility is that our universe may be just one of many in a vast multiverse, with each universe having its own distinct physical laws and constants. The idea of the multiverse arises from theories such as string theory and inflationary cosmology, which suggest that our universe could be one bubble among many in a larger cosmic landscape. String theory, for example, proposes that fundamental particles are not point-like objects but rather tiny vibrating strings of energy. These strings exist in multiple dimensions beyond the familiar four dimensions of spacetime, and string theory seeks to unify all known forces of nature, including gravity, into a single theoretical framework, a goal that remains a focal point of intense research. Inflationary cosmology, on the other hand, suggests that the rapid expansion of the universe during the inflationary epoch could have led to the creation of multiple pocket universes within a larger expanding space. Each pocket universe could have different physical properties, giving rise to a diversity of universes within the multiverse. The idea of a multiverse raises profound questions about the nature of existence and the origin of physical laws. If the multiverse theory is true, it implies that our universe is just one of an infinite number of possible outcomes, challenging the traditional notion of a unique and distinct cosmic origin and prompting us to reconsider our place in the broader framework of reality. Beyond theoretical domains, observational cosmology continues to provide new insights into the structure and history of the universe. Advanced telescopes and observatories such as the Hubble Space Telescope, the Atacama Large Millimeter/Submillimeter Array (ALMA), and the James Webb Space Telescope (JWST), have allowed astronomers to study distant galaxies, map the distribution of dark matter, and observe the luminosity of the Big Bang with unprecedented clarity. The study of dark matter and dark energy, together accounting for about 95% of the universe's total energy density, remains one of the most pressing challenges in modern cosmology. Dark matter, which does not emit, absorb, or reflect light, is inferred from its gravitational effects on visible matter and light. Its presence is thought to play a crucial role in the formation and evolution of galaxies and larger cosmic structures. Dark energy, on the other hand, is a mysterious form of energy that permeates space and is driving the accelerated expansion of the universe. Discovered in the late 1990s through observations of distant supernovae, dark energy remains poorly understood, with various theories ranging from modifications of Einstein's theory of gravity to exotic forms of vacuum energy. The study of cosmic microwave background radiation has provided a wealth of information about the early universe. Minute variations in the temperature and polarization of the CMB, observed by satellites such as the Planck satellite, offer clues about the distribution of matter and energy shortly after the Big Bang. These variations are believed to be the seeds from which galaxies and large-scale structures formed over billions of years. In summary, while the Big Bang theory provides a robust framework for understanding the origins and early evolution of the universe, it leaves many questions unanswered. The exploration of concepts like the multiverse, dark matter, and dark energy, as well as the continued investigation of the cosmic microwave background, promises to shed light on the most fundamental mysteries of the cosmos and deepen our understanding of the universe's past, present, and future. The origins and structure of the universe continue to be subjects of intense debate and investigation. A key question is whether the universe began from a singular, catastrophic event like the Big Bang or if it follows a different cycle, such as in cyclic or quantum cosmology theories. In the context of circle quantum cosmology, CQC, a theory derived from quantum gravity, it is suggested that the universe might not have originated from a single, infinitely dense point. Instead, CQC proposes a minimal length scale, around 1.0 times 10 to the power of -35 meters, beyond which classical ideas of space and time cease to be applicable. According to this model, the Big Bang could never have occurred in the traditional sense, as the universe would not have been compressed to such a minuscule, dense state. Instead, it might have undergone a contraction, followed by a rebound or bounce, much like a phoenix rising from the ashes. The concept of a big bounce is not entirely new, but CQC offers a more formal mathematical framework for it, suggesting that the early universe could have had a low energy density and temperature. This would align with observations of slight temperature fluctuations in the cosmic microwave background, CMB, the faint radiation that fills the universe, which supports the idea of the universe's origins. CQC's approach provides a compelling and potentially groundbreaking explanation for some long-standing cosmological anomalies. It could offer insights into issues such as the asymmetry in temperature across different parts of the CMB sky and the potential role of quantum gravity in shaping the early universe. This model also aligns with recent developments in cosmology, which propose that the universe's earliest moments may have been influenced by quantum fluctuations and gravitational effects. Despite these intriguing possibilities, questions remain about the nature of the universe's beginning. The concept of cyclic cosmology, where the universe undergoes endless cycles of expansion and contraction, presents challenges, especially regarding the accumulation of entropy, the measure of disorder, with each cycle. This increasing entropy would theoretically render the idea of a timeless, eternal universe problematic. The inflationary period in the universe's early history offers another layer of complexity. During inflation, the universe expanded at an exponential rate, filling space with energy that gradually converted into matter. This period, which occurred before the so-called Big Bang, saw the universe grow from a hot, dense state into the cosmos we observe today. The traditional view that the Big Bang marked the beginning of everything is now being reconsidered, with some physicists proposing that the universe may have gone through previous stages of contraction before the current cycle began. Further complicating our understanding, observations of the CMB and the distribution of galaxies have revealed inconsistencies that challenge the conventional Big Bang model. These anomalies include unexpected temperature variations in the CMB and irregularities in the large-scale distribution of matter. These findings have spurred the development of alternative theories, such as circle quantum cosmology, which attempts to merge quantum mechanics with general relativity to describe the universe's earliest moments. The idea of a minimum size beyond which classical concepts of beginning and end no longer apply suggests that the traditional framework for understanding the universe's origins may need to be revisited. While the Big Bang theory remains the dominant explanation for the universe's beginnings, ongoing research and new discoveries continue to challenge this view and may ultimately lead to a more comprehensive understanding of the universe's true nature. Whether the universe had a definitive beginning or has existed in some form forever is a profound question that drives much of modern cosmological research. Our understanding of the universe as a vast, complex entity continues to evolve, offering exciting possibilities for new theories and discoveries.